Hey programmers, Alvin here. Right now I want to go over a Python solution for this Tribonacci problem. So we'll jump right in, really just a spin-off of course, that fib problem. So I'll start with my base cases. I have three of them over here. So first base case, if I have n equal to 0 or n equal to 1, then in either case, the 0th and first Fibonacci numbers are both 0. Right? My other base case is if n is 2, then the second Fibonacci number is just 1. And using those scenarios as my basis, what I can do is now have my recursive call. I can just return the sum of the previous three Fibonacci numbers, right? So I can call Tribonacci of n minus 1 and add that to n minus 2 and n minus 3, of course. So why don't we just run this code, test it out. And I should probably time out because we already know that this gives us an exponential 3 to the n complexity. And we'll probably need to memoize this one. Cool, yeah, it looks like we fail example 07. If I look at that test case, the 7th example gives us an input of 37, which is fairly large, right? Especially given an exponential runtime. So let's go ahead and memoize this to see if we can pass that last example over there. And so you should be familiar with this pattern a little bit by now. So what I'll do is I'll be sure to maybe refactor this. I'll make this my helper function. So just really quick, I'll put an underscore in front of it. It's still a valid Python function name. And I want my main function to be called Tribonacci. Tribonacci takes an n. And all I want to do is really just invoke the helper function now. So I'll just return underscore Tribonacci and pass along the original argument n, but in addition to that, I need to pass along a nice new and empty memo dictionary. So there it is. And now I can take that in for my helper. So over here, I'll take in and pass along that memo dictionary. And again, I'm using a dictionary here in Python because it has a very fast lookup. It's a hashed data structure, so it's going to give me an O of 1 lookup time. And when you're in an interview, I think it's really important to actually mention and defend why you're choosing specific data structures, right? Show that you are knowledgeable about the material. So I'll start by adding an additional base case. So if my argument n is in the memo, that means that I've encountered like this subtree in the visual, or I've encountered this input before. So I just want to return the stored value in the memo. Cool. And in addition to that, now when I have my return line, I'll just take this expression, whatever it evaluates to, store that in my memo. So memo of n equals that thing, and then still complete the same old return. So I can just do that by keying into my dictionary using that same n as the key. So again, recall that our dictionary has keys that represent arguments to our recursive function, and the associated values are going to represent the return value for that argument. So with that change, let's give it a shot now. See how far we get. Nice. It looks like we're able to pass all of the examples in a reasonable runtime. Cool. So it's about the second or third time you've seen this kind of classic Fibonacci-like memoization strategy. We're probably going to increase the difficulty for the following problems, but it should really, really rely heavily on this core pattern, right? So typically when we kind of go through these memoization problems, we'll start with a brute force algorithm, typically recursive, and then it's just a matter of adding our nice memo logic, and you always make the same changes, right? Add your base case, add your logic to store data into your memo, and be sure to pass in a dictionary that is shared for all of your recursive calls, right? And so if you had any issues implementing this Tribonacci problem, I recommend that you try it again on your own. Really have some confidence in your ability to code this problem because it will get more difficult in the next few sections.